The concordance function measures the extent to which two variables move in the same direction. So if I have this thing here, it translates to the probability of concordance minus the probability of discordance. Obviously, that means discordance is the opposite of concordance, right? So in simple terms, concordance is when x1 minus x2, the difference of between two x's that have the same distribution multiplied by the difference between two y random variables that have the same distribution will give me a positive number, right? This captures the idea of moving in the same direction, because if x is greater than x2 is greater than x1 and y2 is greater than y1, then moving from x1 to x2 we are moving up, so it's an upwards movement, so it's the same direction. But if it's a flip direction, then we get a negative product, which is now the event of a discordance. When x1 minus x2 times y1 minus y2 gives me a negative number, right? And then obviously if we look at these two events, we can see that they are complements, right? And when they are complements, if we call this guy event A to avoid writing too much, let's call him A. That means that I have the probability of A minus the probability of the complement of A, which is the same as the probability of A minus 1 minus the probability of A, which will obviously give you 2 times the probability of A minus 1, right? So we understand where the 2 minus times probability of A minus 1 comes from. And then we have to talk about this event now. So if I have the event that x1 minus x2 times y1 minus y2 gives me a positive number, it could either mean that both are negative or both are positive, right? That's the only way to get a positive number: negative, negative, or positive, positive. And in the case of both being negative, that means I have x1 less than x2, right? And then I have y1 less than y2. And in the case of them being positive, I have x1 being greater than x2 and y1 being greater than y2, right? So when we talk about the event A, we have to split, remember A is this guy, we have to split it up into two events, right? The event that I'm not gonna write this again, let's just do this. The event that this guy, gonna copy, yeah, the event that both are negative and the event that both are positive. So this or that, right? Meaning that the probability of A, and remember the probability of A is the probability of concordance, right? Or the event of concordance rather. The set of outcomes that will give me concordance, right? In this case, then I have to split the probabilities. So if I call this probability A1, not probability, event, I call this event A2. then the probability of A will be the probability of A1 plus the probability of A2. And we cannot have an intersection between the two because I can't have both negative and both positive at the same time, right? So the intersection is 0. So they are, I forgot what they call them, complementary or something. No. Mutually exclusive, right? So now I'm going to prove to you that the probability of A1 is the same as the probability of A2, and therefore the probability of A is the same as twice the probability of A1, which is the same as twice the probability of A2, right? To go on this journey, we have to start by picking one of these two. You don't have to know which one you're going to start with. But we can, so for the convenience of the proof, I'm going to pick this one. And I'll show you why. Right? So let's say we want to calculate the probability that x1 is greater than x2, and that y1 is greater than y2, right? Because that's what this describes here. So to start, we have to acknowledge the fact that what we are doing here is that we are finding an expectation, and I'll show you how. So you will probably agree with me if I tell you this, right? That the probability of the event A is the same as, sorry, not the probability, the expectation, right? The expectation so let me not say the expectation of A because that's weird. The expectation of X, the random variable X, is the same as the expectation of X given Y. How do we know this? Because this is the I forgot what they call it, the law of total expectation, right? And there's a proof for it. I will do the proof for it in the next video, right? You can either prove it using integrals or using some notation, depending on whether you are taking on the assumption of a discrete or continuous random variable. But we are not there. We are going to use this to show what I'm about to show you now, right? So now we also know that the expectation of IA is the probability of A. The indicator function, if we take the expectation of the indicator function, which switches on when we have the event A, by switch on I mean it's equal to 1. That means that the expectation of that indicator function will be equal to the probability of event A occurring. And also, we know that the expectation of A given B is the same as the probability of A given B. Using the same logic, now you're going to just use what you call conditional probabilities. It's the same logic, right? Now, that means you agree with me if I tell you that the expectation using this above law, the law of total expectation, say the expectation of IA is equal to the expectation of IA given B. I have not changed anything, have I? I haven't changed anything. I have just written it in a different form. Now your X is IA and your Y is B, right? And B represents information, right? And then now that means it simplifies to the probability of event A being equal to the expectation of the probability of event A given B. Done. This is very important when we come here now, because I'm going to apply it. So So let me just shift this thing to the side. We are going to apply the law here. We'll call this event A. No, it already has a name, right? It was event 2 or something, but it's not important. This is the expectation of the probability of x being less than or greater than x2, y1 being greater than y2, given x2, and we can use a comma for end to avoid writing too much, and y2 like that, which would obviously mean that we are finding the expectation of this brother with respect to these guys. So if you write it in integral form, we have double integrals. Why? Because we're dealing with two variables, x and y. This r here means from negative infinity to infinity. For lazy people, the expectation of the probability that x1 is greater than x2 and y1 is greater than y2, given that x2, now we give it a value because we are going to be summing over this x, right? And also we're going to be summing over this small y, because now we're finding the expectation of this guy, this whole thing, given each possible value of x and y, right? And then you're going to multiply by the joint PDF of x and y. And be careful here because we're dealing with x2 and y2, but it's not important in the case of x1 and x2 having the same distribution. But let's assume that they don't have the same distribution, so I'm going to classify them and say that it's x2 and y2, xy dx dy, right? And then you're going to find yourself with double integrals. This is r x1. We can now substitute this guy here, right? And see the probability that x1 is greater than x and y1 is greater than y, small y, multiplied by this guy times dx dy. And then we're going to apply a transformation. We are going to say that now be careful of this, ne? It's a transformation, so let x, ne, fed into the CDF of x2 or x, let it be equal to u, and let fy small y be equal to v. So that clearly means that d, when we differentiate both sides, or let's put it this way, is going to be du, and dfy is going to be dv. Understand? So we can now proceed by substituting copular notation in this whole thing. say that this guy here, he's the same as, so this guy is very special actually. Let's speak about him on the side. If I tell you that I have two events, né? An event, let's call them event C and event D. And event C is that x is greater than, okay, let's say if x is less than small x, and event D is that y is smaller than small y. If I want, and remember, this is a Venn diagram, so it's the whole thing. You must be careful because the probability, or rather this event here, the intersection, right? Or let me even use a nice annotation. The intersection of event C and event D is not equal to the complement of, it's not equal to the complement of this event here. They're not the same. The reason for this is that if we go and shade this event here, we're going to shade here, right? That's event C intersected with D. But now you want the probability that x is greater than small x and y is greater than small x. So what we want is, we want the probability of an intersection of the complement of C and D, right? So this guy here, which I'm going to shade with blue, is the outside. He is the outside. So that means that the probability that x, let me just use probability now. The probability that x is greater than small x and y is greater than small x is going to be equal to 1 minus the probability that x is less than small x, not and, but or y is smaller than small y, right? Which will obviously be equal to the probability that x, remember this means that, right? Plus this minus that. Yeah, well, which is the intersection now. So you're just going to have this. As you can see, they are not complements. So you're going to apply it here, right? So, and now we're going to use copular notation. So this is going to simplify to 1 minus u minus v plus c, and it's c1 u v. And then here it's going to be small c2 u v du dv. That's after the transformation, right? And then we're going to see that this number 1 here is going to be a sum over all of the possible values of C2, which will obviously result in 1, because we know that when we sum a PDF across all of the values of the random variable, we get 1. The same logic applies to joint variables, or sorry, to joint distributions. The same logic applies. And the next one is going to give us the expectation of U, because we have U times PDF. And the next one also is going to give us the expectation of V minus this very special integral here, which is the remaining part now, right? Ish. And we just left with this. And in this case, we all remember U is this, and we know that the CDF ranges between 0 and 1. And if you apply a CDF transform to a random variable, the resulting transformation will be uniformly distributed between 0 and 1. And we know that the expected value of a uniformly distributed random variable will be the sum of the endpoints, which is 0 and 1, divided by 2. And clearly that's half, right? And let's call this integral, we're going to call this integral, I don't know, let's call it I for now. And as you can see, we have cancellation. And that's just going to give us 0, so we just left with I, right? Which is, from now, I'm just going to use this notation. It means the same thing. C1, U, V, C2, U, V, du, dv. But now, if we reverse the transformation, we're going to go back to, oh, by the way, this is wrong. I'm supposed to say from 0 to 1, because I've applied the transformation. So from the moment that I start introducing U and V, my U and V range between 0 and 1. Although technically I wouldn't be incorrect if I was to still keep my infinity, because still I will be covering everything, right? But it's more correct to say 0 to 1, and it's more rigorous, right? But if I now reverse the transformations and I go back to X and Y instead of U and V, I am left with a CDF of fx1, sorry, y1, x, y, and then here's PDF x2, y2, x, y over x and y, right? And this is very clearly the expectation of the probability that x1 is less than x2 and y1 is less than y2, given that y, or given x2 and y2, which is then going to give us the probability that x1 is less than x2 and that y1 is less than y2 by the law of total expectation. So I've shown that this guy, see the signs are flipped, and that guy are equal. And then that means I can move forward to say that that means that Q, C1, C2 will just be the two. Remember, we had this initially, right? So now I'll just simplify it to 2 times 2 times the probability. You can choose one between these two, doesn't matter. You're going to get the same integral. In fact, let's just, okay, it's fine. what do I do? Let's see, this is when they're both what, negative or positive, it doesn't matter. Let me just write it out. I'm lazy, but let me just write it out. This is the case. Minus 1, and I know this before, times double integral from 0 to 1 of C1 UV multiplied by the PDF, joint PDF of U and V using the second copula. If they're not the same, then you apply it that way. So this notation is shorthand for this notation here. It's the same thing, right? And you will also find, or minus 1, you will also find that if you reverse the rows, it's the same thing. If I say C2 UV times D C1 UV minus 1, it's all the same thing. So this guy is a very important thing. And then one very interesting fact is that this guy is the concordance function, right? It's the concordance function of x and y, but for the same copula, like this, right? We maintain the same copula throughout. So that's the Kendall tau. This is Kendall tau, and I'm going to be talking about the estimation of, or the estimator of the Kendall tau when we have a sample. And we use the idea of ranks to show this, but that's another story. Otherwise, we have shown and proved the formula of the concordance function. Thank you.